All right, testing. Can you hear me now? How's that looking? Oh, sounding perfect. Thank you, guys. All right. Thank you, everyone, for checking on that for me. So, yeah, welcome to algorithms. So this course is Comp 3121 for undergraduates and Comp 9101 for postgrads. It's combined as a single course, and you basically do everything together. We'll give people another minute or two to show up, and then we'll get underway. I've noticed the first error on the slides already. I've forgotten to update this from term 1 to term 2 in my template, so I'll get that fixed. For those who'd like to follow along with a copy of the slides yourselves, you can find these slides on Moodle. I've uploaded them as of a few minutes ago under the lecture slides and readings section. Hello, everyone. Yeah, I don't know. This is how I'm used to working. This is how I'm used to teaching. You know, this was like $100 or so at Officeworks, and it served me well for a good year or so. Yeah, so the way this will work is we'll switch between the slides and the board, like so, and when we need to draw stuff, we will do so. All right. Yeah, so marks. We will talk about marks shortly. Okay. It's 4:02, which means we'll give people another little bit longer. Yeah, so how to win hacker rank. Look, certainly this course will give you some a starting point at least for those kinds of sites, but as you may be aware, there is no programming in this course, contrary to what the title of the undergrad course says. So yeah, look, if you're interested in more of that kind of stuff, certainly this gives you the fundamentals in terms of knowledge and reasoning about algorithms, and then implementation is not something that we're going to cover in this course, but you'll learn that in the rest of your degree. Okay. All right. I guess we can get started. I'm sure a couple more people will trickle in over the next minute or two, and then yeah. So, welcome to Algorithms, Comp 3121/9101. My name's Raveen. Pronouns are he, him. Here's my email address. My office is also listed here, but I'm almost never in the office. So, if you want to see me face to face, you'll need to email me first. The course admin for this course is Anna. If you want to contact Anna and myself, please email the class account cs3121@CSE. That goes to both of us. You do not need to really, in almost any other circumstances, contact either me or Anna directly. All right. So email the class account if you have any questions. All right. It is not term 1. It is term 2. Sorry about that. So we're gonna have to start off with some admin stuff and just tick off the fundamentals, and then we'll get into some examples and some problem solving later today. So what do you need to start in this course? First of all, you need to be aware of data structures and algorithms that you've seen in your earlier courses. So these include things like arrays, trees, heaps, sorting and searching algorithms, and so on. We will have some brief revision of this in tomorrow's lecture, but again, that will be an overview of what we need to have learned previously. You can consult your materials from Comp 2521 or equivalent for more details here. Importantly, this is an entirely written course. There is no programming. There's no coding. So you do need written communication skills throughout this course in order to reason about your algorithms. If you are interested in applying these ideas in code, you can go on to do later courses like Comp 4121, which is advanced algorithms, and Comp 4128 programming challenges. I'll come back to these a couple of times during the course, but Comp 4121 is applying these ideas into bigger and more real-world systems, and learning some more involved mathematics to do with them. And Comp 4128 is programming challenges where we solve some very small self-contained kind of problems in a competitive programming kind of situation. I teach Comp 4128. It runs in T3 every year. I believe, I'm not sure who is teaching Comp 4121 this year. That also runs in T3. I'll mention this here and it will come up again. If you want help with writing, especially for assignments, there is a resource called UNSW Smart Thinking. You can click the link for more information on that, but basically they will review your draft assignments and so on. This is a legitimate service that is offered by the university. We will have a chat later on about illegitimate services, shall we say, and academic misconduct and things like that. But that's a first point of call for help with writing. Okay. In terms of prerequisite courses, the only formal prerequisite is that you've done Comp 2521 or 9024. However, there are some additional points of knowledge that are useful. We don't officially require them, but we recommend that you consider taking discrete maths or foundations of computer science, depending on your career, before you come into this course, because it will help you with this, with some of both the theory and the practice of writing formal arguments. Certainly the skills that you pick up in those courses will be very useful here. Furthermore, if you're an undergrad, doing first year maths before coming into this course will help a bit in terms of your familiarity with matrices, complex numbers and limits, although again it's not specifically required. Welcome. Okay. I'll mention here that if you have any questions about enrollment, so for example, if you're tuning into this but you're not yet formally enrolled, enrollment queries have to go to the Student Hub. I personally can't really do anything about them. So as much as I'd like to help, send it to the Student Hub. So complex numbers are mentioned here. They might come up once or twice. They are the main application of complex numbers that is sometimes taught in this course is in the fast Fourier transform, and we're not doing that this term. So it's good to be aware of it, but it may incidentally crop up, not a main focus of the course at all. Okay. Here I do need to tell you about the other course in this line, which is the extended version of this course. So Comp 3821/9801 for postgrads runs in T1 of every year. There are some differences in content and in assessment, so they do more content and they do more assessment, to put it briefly. So some of the later topics that we do, they do in more depth, and the assessments they do generally harder assessments, and they also have some extra group assessments. So I need to mention this because we do have to do some adjustments to marks to keep it fair. We don't want the very top students to be doing the lower course for WAM reasons. So at the very top end, we will have a little bit of scaling down. Now, let me be as clear as I can about this. If you get anything below a HD equivalent mark, that will only ever go up, okay? So anything below an 85 will not be scaled down under any circumstances. Anything above an 85 may go down a little bit, depending on what the marks distribution is. So for example, we did this exact same kind of scaling last term when both 3121 and 3821 were running. In the end, in comp 3121, we ended up having, let me try and remember. I think the maximum mark you could get was 99. So it was possible to get 99, and there were like 6 people who got 94 or better. Now, no, if you will not get scaled down below 85. Certainly, all the scaling is monotonic, obviously. Really, if you're in the 85 to 90 range, you can expect that things will run at about your scale mark will be about the same. If you're above 90, you may go down 1 or 2. That's basically what we're working with. Yeah, so I understand that there's a couple of people who may have to do 3121 in other terms for timetabling reasons. Again, if you're getting something in the order of a 94, 95, if you're one of these top students, then I hope that's not too big of a deal, right? Again, 6 people got 94 and above last term, so hopefully not a big deal at the top end. But again, I can't stress enough, this really only affects a handful of students at the most. Almost everyone is going up, and there's a couple of % at the top who might go down 1 or 2 marks. The average final result in T1, I don't remember off the top of my head. I can check that out for you in the break. So if you have, if your raw mark is below 85, it will not go down. If your raw mark is above 85, it may go down, but only it certainly won't go below 85 because, again, I'm not going to scale you down below people who got less than you in the raw result. 6 people got it after scaling. So there were 6 marks of 94 and above. Again, if you're a top student who is doing this course, hopefully something like a 94, 95 is not the end of the world. So yeah. And I think Wayward has the right idea here. Do your best. If there are many good performances, I'm more than happy to give I'm more than happy to give more than 6 high marks. But again, I'll be trying to match roughly the distribution of WAMs coming into this course. Again, with the proviso that people who are in the 95 plus WAM should really consider taking 3121 instead of this course. If you really have serious concerns about this, send me an email and I'll see what I can do. All right. Cool. Again, I just have to reiterate, if you're being affected by this, you're in the top 1% of students. Yeah. On the other hand, what will affect many more students is that there typically is a fair amount of scaling up at the lower end. So yes, it is absolutely possible to get 90 plus. There won't be heaps of 90 pluses, and I won't be giving out 10 marks of 100 in this course, precisely because there is an extended course, and some of those students should, in that situation, some of those students should have done the extended course, right? But yeah, it's entirely possible to get 90 plus. It's entirely possible to get HDs. I'll be, again, aiming to roughly replicate the distribution of your WAMs starting the course. Okay, in any case, fail rate last term was something in the order of 5 to 10%. But again, this included a dozen people who didn't attempt the final exam, for example. So so not substantially higher than other courses of second, third year at CSE. Okay. Anyway, we'll come back to assessment, but for now, let's talk about classes. So this lecture runs at 4 p.m. every week, and tomorrow morning we have a lecture at 11 a.m. every week. Week 6 is flexibility week, so during week 6, we won't have lectures introducing new material. We very likely will have at least one revision lecture in week 6, but I'll confirm that closer to the date. Off the top of my head, I can do the Thursday afternoon, but not the Friday in that week. Yeah, so most likely the Thursday afternoon of week 6 will be a revision lecture, and the Friday morning of week 6 will be nothing. Okay, live streams and recordings are on YouTube. If you're hearing this, you found it. The slides will be uploaded to Moodle before classes begin. I'll also be running consultation on Tuesday and Friday afternoons. These will be live on Zoom. You can find the link in the welcome announcement on Moodle. Consults will be recorded and the recordings will be published to YouTube. Closer to exams, I will have consult like every weekday, more or less. I'll publish a schedule of that closer to the date. Okay. So now to answer Long's question, how to do well in this course. Of course, there is a fair amount of, I think a lot of it is practice, but also you need to get help sometimes. Everyone needs help sometimes, and that's good and fine. The first thing that I can suggest is that you join the Ed Forum. Here you can discuss course material with other students and with staff. In this course, you may have noticed there are no scheduled timetable tutorials or labs. However, we are running some help sessions. So every weekday starting next week at 11 and 5, except where it clashes with lectures, we'll have a tutor discussing some tutorial problems, and you can come along to these whenever you like or not. Wayward asked about in-person classes. We are going to have a couple of these in person. So I'm still waiting on room bookings for this, but at this stage I expect the Tuesday afternoon and the Friday afternoon sessions to be in person on campus somewhere. That will be you'll be informed of that when that happens. The others will be on Zoom, and they will be recorded. You can come along to these. The tutors will have prepped a couple of problems that they want to discuss from the tutorial exercises, but you can also bring your own requests, and they'll do their best to present those as well. Speaking of tutorial exercises, I'll come back to that shortly. Other questions discussed different each day, most likely. We haven't finalized that yet, but we won't be repeating the same questions over and over again, especially because there is a recording. We'll try not to duplicate things too much. We'll see if we can publish some kind of rough guide of what's going to be done every day. I'll follow up on that. Sure. The extended course isn't running right now. It only runs in T1. So So in this term, that doesn't really come up. Yeah. Okay. Let's talk about assessment. Unfortunately, we've got to do this. In this course, we have 4 written assignments. They are released every 2 weeks. So there'll be assignments released in weeks 1, 3, 5, and 7, and due 2 weeks later, weeks 3, 5, 7, and 9. Each assignment will have 4 questions, and those questions will have some subparts. And each of your 4 assignments is 15% of your course mark. The first of these assignments has been released as of 4 p.m. today. Then the final exam at the end of the course is the only other assessment. It's a 3-hour exam consisting of 8 multiple choice questions and 4 extended response assignment type questions. The final exam is conducted on Inspera, which is UNSW's online exam platform, and the final exam is 40% of the course mark. In addition to this, there's up to 5 bonus marks for forum participation. So we'll give out some marks to roughly the top, again, 5 to 10% contributors to the forum. We will reward quality more than quantity, so trying to unhelpful contributions, we will sift out some of that. But typically the top 5-ish% of students will get at least 1 mark, and then about half that number of students will get 2 marks. Half again will get 3 marks, and so on, as a guide. So we end up having only 1 or 2 students who are really top contributors to the forum, providing regular useful insights, getting the full 5 marks, and many more getting 1 to 2 marks. Okay, there's a few questions here, as I might expect. All right, let's just scroll up a bit because I'm losing it. Okay, KA asks, would you say we need to watch or attend all of the help sessions? Generally, no. So attend or watch as many as you feel are necessary. It basically depends on how you're going with the tutorial exercises. So speaking of the tutorial exercises, we will be publishing 5 or 6. We'll confirm that 5 or 6 sets of tutorial exercises, which will be a few pages of practice problems. The first set of these will be released tonight, probably soon after the lecture concludes. And so you can work on these in your own time. They are not assessed, but you can feel free to discuss them on the Ed forum and with other students freely. And then some of those problems, the selected problems from those lists, will be discussed in the help sessions, as well as you can take your own selection of problems from those tutorial exercises and request them in a help session. So yeah, to be very transparent, last term the attendance in the help sessions was very low. It was it was much lower than we'd anticipated. But the few students who did attend regularly reported, especially in their My Experience feedback, that they found it very helpful and they got a lot out of it. So I recommend that you at least try to show up to one of these a week. Again, they're running every day, so hopefully there's at least 1 or 2 that can fit your schedule. Is the link to the Ed forum on Moodle? Yes, it is. It's also in the slides. Assignment weighting is a lot, yeah. In the past, it has been. In the past, the assignment weighting was only 40%, and if you go back a few more years, it was less still. But we did have some feedback asking us to reduce the weight of the exam and increase the weight on the assignments. Yeah, we've responded to that. So just as it was last time, the assignments are 60%, the exam is 40%. Multiple choice in the final, yeah, it's intended for you to get some easier marks. The multiple choice definitely are the easier marks in the final exam. And the average in last term's final exam was higher for the multiple choice than the rest of the exam. Does Inspera spy on us? No, it doesn't. It's not proctored at all. Oh, Song's here. Thank you so much, Song. So Song's one of our most senior tutors. He's the main forum moderator. So you'll have lots of contact with Song throughout the term as well. Yeah, so Inspera doesn't do any kind of proctoring. There's no webcam, no microphone, no nothing. It's, there will be more details on Inspera later on. No hurdle for the assignment, that's correct. So for the exam, you can in theory pass the course with 0% on the exam. Assignment submissions are on Moodle, that's correct. And the amount of writing that we expect in assignments is typically about, we say less than a page for each of the 4 questions, which is not a hard limit. You can write a bit more if you want to, or if it's suitable for the approach you're trying. But as a rough guide, if you're writing more than 2 pages, you're overcomplicating. So there's no word count or anything. As a guide, you should not need to write much more than a page. Assignment submissions on Moodle. Wayward, I'm not sure what that question means about students having all the answers. But bonus marks are awarded for asking good questions, absolutely. tutorial questions, yes, there will be solutions provided. In the past, we've kind of held off on releasing solutions until a bit later for fear of spoiling questions. This term, I'm going to try releasing the solutions a little earlier than in the past, so we'll release the first set of tutorial exercises tonight, and you can expect the solutions to those to be published like around the weekend. So we'll give you a couple of days to work on them in your own time if you like, and then we'll give the solutions pretty soon. No, nothing is handwritten on this course. Everything must be typed. Anthony, everything has to be typed. There's a couple of reasons for this. One is that handwriting can be difficult to read. Also, we do need to do some plagiarism checking, and this is obviously more difficult with handwritten submissions. So yeah, everything must be typed. On that note, we recommend that you use LaTeX. With your enrollment, you get a free professional account on Overleaf, which is a collaborative typesetting service. We will also be publishing some templates for you to start from, so that you don't have to retype the question and things like this. So that will be hopefully helpful for you to start. Hopefully that will be useful for you to start writing your assignment submissions in LaTeX. Okay, 2 pages is not a limit, it's a guide. Again, if you are writing more than 2 pages, it's fine, we will read it, but you've probably overcomplicated something, because it should be possible to write a concise solution in much less than that. Tutorial problems will come out when we've covered the relevant material. So the first set is on introduction/revision of old material, and so that covers the first 2 lectures in the course. And so the first set of tutorial exercises will be out today. The second set of tutorial exercises covers divide and conquer, which is the next 2 lectures, so week 2 lectures. And for that reason, tutorial 2 will be out next week. The first assignment covers both those topics. So in that first assignment, there are a couple of questions that you'll only learn the relevant material for next week. So there are some questions that you can do already, but by all means get stuck in. There's 1 or 2 questions where you may struggle to get started because you haven't seen the relevant material. Hold off until Thursday or Friday next week for those. Okay. Expected format for the submission of the assignments? Tutorial solutions. That's it. I'll talk about this soon, but we've written up tutorial solutions to a higher standard, to the standard that we expect for assignments, and so that's what you can model your solutions off. Okay. Hanxian, haven't received any emails. There was one announcement email that was published a few days ago, but perhaps you didn't have Moodle yet, in which case you wouldn't have received that email. There's no problem there. Okay. Yeah, actually, this is a good point. I do need to mention some stuff about misconduct here. So in the assignments must how to put it. So you can discuss. This is all written up in the in each assignment section on Moodle, so you will see it when you click through to find the assignment questions. But as a general rule, the assignments have to be your own work. What that means is you can discuss the assignment problems at a high level with other students privately. That's fine. You should acknowledge any students who you talk to and collaborated with. By writing in your submission, I talked to Z blah 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 name about this problem. And that's perfectly fine. We do not consider this to be misconduct at all. Yeah, in fact, we are very relieved to see this. You can consult. You can use resources from within this course, so our lecture slides and so on. You can refer to that without giving a citation. There's no need. You can refer to either of the 2 textbooks, which we're about to cover, again, by just referring to the appropriate section, and that's fine. So if you dug something out of the CLRS textbook, you can just say section 7.2 of CRS. That's completely fine. If you want to use external resources, which maybe go into a little more detail or something that you found more explanatory, you can do so. You can refer to those external resources as long as those are general resources. So if this is giving you some more detail on a particular algorithm, that's fine. You cannot use external resources that are specific to the question that is being asked of you. Yeah? So you can't like, if you find this question, the exact same question, find this exact same question on some forum or something, you obviously can't just give us a link to the forum and say, oh, here you go, right? This is obviously not this is not a useful way of doing an assignment. Yeah, but if you do find some general resources which are helpful for you, you must reproduce that in your own words and give us a reference. Okay, because we need to know that you've understood it as well as where it's come from. Okay. As for the final exam, broadly similar. So again, yeah, sorry, I've forgotten to mention the most important thing. This is what I've talked about in terms of external resources and talking to people about the assignment. This is all fine, but your write-up must be done by yourself. Okay? Is that clear? So you can talk about it with your friend, that's okay, but at the end of the day, you have to write up the assignments. You have to write up your submission yourself. Do not show your draft or final submissions to anyone except the UNSW Smart Thinking Service if you are using it. If you share your submission with your friend and your friend then copies it down and submits that as well, you are both guilty. You can both be found guilty of academic misconduct, and the penalties for academic misconduct, including things like collusion, but also contract cheating, like copying answers off forums and things like this. These penalties are quite severe. They can range up to 0 for the assignment, 0 fail for the course, or expulsion from the university in severe circumstances. So in terms of asking course staff for help, we can give you very limited guidance. What that means typically is that we're very happy to answer things about clarification of the questions. If you're unsure about what the question means, you absolutely can post about that on the forum, and we'll help you out with that. You can share examples to help others understand the question. That's fine. If you want to share test cases that you found useful for you, that's okay. But again, if you're asking, hey, my idea is this, is that correct? I can't answer that because I can't answer that for everyone, and I don't have time to answer 600 people about that, and it's unfair for me to answer some but not others. Okay, so we can clarify the question for you, but we can't tell you what to do. However, halfway through the 2-week duration of each assignment, there will be some clarifications published from the Ed Forum, as well as a hints for selected questions. Okay, advice for how to do well in the course. Tutorial problems are the big one. You have to practice. We'll come back to this, but I can tell you about algorithms in lectures, and that's all well and good, and you can do assignment problems, but you have to practice. You have to do lots of problems yourself. And again, the biggest source of this is the tutorial problems and also the textbooks. Okay, and be active on the forum and come to help sessions. The more you talk to other people, staff and students about the course, most likely the better you'll do. Okay, so I hope that's covered all the questions about assessment for now. I'm sure there will be more as we go on, but yeah. All right, let's continue. I'll make you a mod at the break song. Thank you. There are 2 textbooks that are recommended for this course. The main one that I recommend is Algorithm Design by Kleinberg and Tardosh. There's a paperback version of this textbook now available at the UNSW Bookshop. It is also available not at the UNSW Bookshop, if you know what I mean. Algorithm Design is a really nice textbook to read. but it's not as complete as the other textbook CLRS, which is more useful for later on in your studies and your career if you need to look things up. You can find a greater breadth and depth of algorithms in CLRS. So the alternative textbook is Introduction to Algorithms, the famous CLRS textbook. The third edition is available at the bookshop. The fourth edition, I was recently informed, was published like a month or two ago. It's not yet available at the bookshop. And yeah, this is a very complete textbook, but it's a bit difficult to read because of the style that they use. It's a bit formal, and so maybe not the. We have a joke that any textbook that starts as any book that's titled Introduction to something is extremely complicated. Yeah, that's certainly no exception here. So I recommend that unless you have some familiarity with algorithms already, or you like a very precise and formal style, you probably would prefer the first of these two textbooks. Okay, I hope that's answered Zia's question. Again, it's a personal preference, but I think for most people, algorithm design is the more useful of the two textbooks because it's a bit easier to read. It's not a proof is left to the reader type of textbook, like CLRS, is the opposite of that. It's that they do all the details of all the proofs, and so it can be a bit dry to read for a beginning reader. First edition is fine for Kleinberg and Tadosh. Neither of them are compulsory. We won't assess you on things that are outside of what's presented in the slides and the tutorial exercises. So you don't need to have either of these, but they are both good as a reference or as supplemental reading. Again, it is optional for you to pick up either of these. Problems in the textbook are definitely helpful in addition to the tutorial problems. In fact, there's very likely to be some commonality between them. Absolutely. These textbooks both have a good selection of additional problems that you can work on. So that's another reason to check these out. Okay. So next up, let's talk about what's different between last term and this term. And I hope this will give you some idea of what the My Experience survey is for. So at the end of each term, we ask you to fill out the My Experience survey, which asks you to rate your experience in the course, as well as give us some feedback, both in terms of what we did well and what can be improved. And so that informs a lot of what we do between terms to improve the course and to take into account what you've asked for and try to deliver on that as best we can. So a couple of things that were requested last term were that the help sessions should be more tutor-led rather than student-led, and so we've listened to that. There was a large request for face-to-face tutorials. Again, getting tutorials scheduled is something that takes time because it has to go through central admin systems. But what we can do in the short term is provide face-to-face help sessions as well as recorded help sessions for those ones that are on Zoom. We'll be implementing that. Again, more details on help sessions to come out in the next couple of days, hopefully. Tutorial exercises. So we were told that some students didn't have quite as clear an idea as they would have liked of what we were expecting in assignments. And so what we've done in response to that is that we've made some changes to the tutorial solutions. We've written them up to an assignment standard, and so as you'll see when the first set of solutions come out, they are pretty complete and they can be used as a model for you to base your own assignment submissions on. The tutorial exercises have also changed. I was told that by a couple of students that the tutorial exercises used to be one big long list of questions for each of the 5 topics, and this was a bit daunting. So we've broken them down into sections by what topic, what technique is being used in each question, as well as we've categorized them as key questions or hard questions, so that you at least have a smaller number of questions to work on to start off with, and you can optionally extend yourself by taking on some more challenging problems. Other things that have changed: the assignment question format. So previously, the assignment questions have just been design an algorithm, 20 marks. We're going to break those up into a couple more subparts. So that will include a couple of easier marks at the top, just to confirm your understanding of the question and build your way up. So we will kind of give you some of the hints as sub-questions rather than releasing verbal hints a week out. So again, hopefully this will help you find the assignments a bit easier to at least get started in. All right, so hopefully hopefully I've convinced you that we are responsive to feedback. If you ask for something, we'll do our best to deliver on it, whether that's immediately or if necessary in the future. And so for that reason, I ask that you please give us your feedback during your experience of the course, which includes the survey that's completed at the end of the term, as well as telling us informally elsewhere. So we do have a pinned thread on Ed, which is asking for your feedback. You can post anonymously on that. If you'd prefer to keep your name hidden, that's completely fine. And so again, we'll do our best to respond to requests for changes in the course. And you can also email us at any time. Again, we'll do our best to respond to feedback whenever you provide it. Again, the more you can tell us about what we're doing well and doing and can improve on, the better we can deliver on our promises to you and to future students. William, it'll depend on the questions. So there's a question in assignment. There's a couple of questions in assignment 1 where the earlier subparts are building blocks and the later subparts use those. There's also a question in assignment 1 where part 3 of the question is an easier version of the same problem as in part 4, and it says there you can skip question 4.3 and just do 4.4, and we will mark your submission for 4.4 as also solving 4.3. Yeah. So in that situation, you do not need to provide 2 different algorithms for the 2 parts of the question, but in question 2, we are asking for specifically 3 different algorithms for 3 different time complexities. When would I recommend you to start assignment 1? I recommend that you read the problems today. Let them turn in the back of your head. If you know how to solve one or more of them, great. At least jot something down. But you may also just improve on that as you go, as you see more lecture material. So yeah, start reading the problems today, and again, work on them in your own time because it is due 2 weeks from today. When would you recommend? Will there be a penalty for writing out of format? Not really. We ask that you write things that are clear, convincing, and correct. And so, as long as what you're writing is easily understood, that's fine. Not sure what you mean by format exactly, but if you'd like to clarify that, I can answer that question later. Yeah, so assignment 1 was released today. The assignment schedule is pretty tight. This is basically a consequence of the fact that our first lecture is on Thursday of week 1, and we need to have the last assignment due in week 9 rather than week 10 so that we can get it back to you in time. All the assignments are hand marked. There's no auto marking, and there are about 600 of you. So as you can hopefully understand, it takes time to it takes time to return those to you because there's a large amount of work that goes on behind the scenes to mark the assignments both quickly and correctly and consistently. So we have a large team of markers and we have some auditing processes so that the marking that we provide you is consistent. In all, this means that it takes about 11 to 12 days at a bare minimum to return those assignment submissions to you. This means that you should get your first assignment back before your second assignment is due. All right. But yeah, it is really one after the other. So you'll submit assignment 1 on the same day that assignment 2 is released. Okay. Yeah. As to Blake's question, the assignment directions, I'm pretty sure, tell you do not submit code under any circumstances. Like, do not submit code; it will not be marked. So any code that's written in any programming language will be ignored. You must write in words. Yeah. Should we do both weeks of tutorial questions before attempting the assignments? No, I recommend that you at least read the assignment first. You should at least have some ideas about some parts of the assignment before doing the tutorial questions, and then do the tutorial questions to develop those skills and practice, and hopefully that will help you solve the remaining assignment problems. No group assignment. Assignment 1 is due on Thursday of week 3. So exactly 2 weeks from today. Faza, you can write code to implement your algorithm if you want to, but we will not be marking your implementation. We will not be marking code. One of the reasons for this is that not all the markers know all programming languages. So yeah, you have to write in words, and if you've done some work on the side to also implement that and confirm that your algorithm does what you think it does, that's up to you. But there's no part of this which is going to be assessed. It's only your writing that's going to be assessed. And the reason for this is fundamentally that to be a good professional computer scientist, you need to be able to solve problems efficiently, but you also need to reason about why your algorithm works, why your algorithm is correct, and why your algorithm runs in the time complexity that you claim it does. You need to be able to explain that to other programmers. You need to be able to explain that to people who don't code. And so that's exactly the kinds of skills that we're going to be developing in this course. That is solving problems using creative and novel ways of applying lecture content and techniques from lectures. But also you need to write convincingly as to why it is correct, why it does what you want it to do, and why it runs in the time complexity that you claim it does. Wayward, no, there is no code in this course. So do not submit code, it will not be marked. Okay. All right, so finally we're through the admin stuff. So I want to present some like an overview of what we're trying to do in this course, and a couple of motivating examples for the rest of today's lecture. So in this course we'll be talking about designing algorithms to solve problems. There will also be some theory, but the main focus of this course is not that you learn a bunch of theory from lectures necessarily, but that you're able to apply that theory to solve unseen problems. So we say this word algorithm a lot. Let's get some precise notion of what exactly it is. An algorithm is a recipe. It's a sequence of steps that you can execute one after the other in a mechanical way. Mechanical here is very important. What we mean is that to implement any of these, like to execute any of these steps, you don't need to think. You don't need to make decisions other than the ones that are specified for you. Yeah, which is what I mean by recipes. Yeah, there's no, we don't say pick the best thing. We say pick the thing that has the most blah blah, right? Because again, we don't want the execution to require any human kind of decision making. And yeah, some trivia here as to the origins of the word algorithm. You can look into that if you like. Cool. Yeah, so a bit of scope narrowing first. In this course, the algorithms that we're going to look at are sequential algorithms, and they're deterministic algorithms. So sequential meaning that it's given as a sequence of steps, and so we will be doing one step, then the next, then the next. This is in contrast to parallel algorithms, where you can be working on several things at once, and this can have implications for the time complexity of your algorithm. If you're interested in studying parallel algorithms, that's a very rich field of study. That's again one of a few next steps from here, and you can. Actually, I'm not sure if any parallel algorithms are still taught in 4121, but it used to be. So parallel algorithms are a rich field of study, but beyond the scope of this course. And similarly, randomized algorithms are also beyond the scope of this course. So we will only be talking about deterministic algorithms which have no element of randomness. All right. So if you're interested in quantum computing and quantum algorithms, again, beyond the scope of this course, hopefully that's obvious. All right. So why do we need to do this course? Why is this course important? Why are the skills that you get out of this course going to help you in your career, in your life? The main idea is that algorithm design is it's a skill, right? It's a skill that you acquire through practice. There are plenty of great resources about algorithms, including the textbooks and online, which will tell you about a whole lot of problems that have already been solved. And of course, these references are useful for learning about algorithms, but in the end, the main skill that we need you to take out of this is to apply those techniques to problems that you have not seen before, that you can't just search for. And so our main goal in this course is to learn techniques and like problem-solving paradigms, which you can then apply to solve unseen problems. So throughout this course, you will see a bunch of algorithm design techniques, as well as the theory underlying those. And then we'll give you examples that illustrate what techniques we're using. The main one is the last one. Your algorithm design skills are the main point that we have to work on in this course. It's not enough to just sit in on lectures and absorb theory. You have to practice, and so practice means do the tutorial exercises, talk about interesting problems that you encounter with your friends and on the forum, go to help sessions and so on. You need to practice. All right. So we're going to let's take a break here, and then I'll come back to okay. Thank you, Song. Thank you so much. Let's take a break here, and we'll come back to an example problem, actually 2 example problems that demonstrate what algorithms are for and how we can use them to solve what look like difficult problems. Okay. So we'll take a break here and we'll start again in 10 minutes. In the meantime, I'm happy to take any questions that you might have from the first hour. I know there's a lot of important information that we've gone over, and again, happy to revise any of that. Thank you so much, Song, and I will add you as a mod in future. So Blake, we use one-base indexing throughout this course. So for arrays, we'll index them by 1 through n rather than 0 through n minus 1. Yeah, look, I'm very much a C++ programmer, so it rankles me too, but it's consistent with the textbooks and so on. So that's the choice we've made, and it's one that we will stick with. So this question is pretty much unrelated to programming. I mean, okay, I say that there are some interesting programming problems related to this, but the problem itself is very intuitive rather than it's not like the programming part of it is not the point of the question, right? So this is something that I hope in fact, I did present to an audience of just other teachers from other faculties last week, and everyone understood what the problem was about. So, yeah, it's very much an introductory type problem, which gives you an overview of how we're going to, how like applied problem solving and reasoning are important in this course, more so than a whole bunch of theory about data structures and algorithms. Okay. All right, Red, I'll ask you to think about that some more, and yeah, perhaps that is the start of a correct solution, perhaps not. That's exactly the kind of thing that we're going to explore throughout this course. In fact, this kind of idea of pick the best looking item at a time is basically the fundamental building block of greedy algorithms, which is something that we're going to cover in week 3 of the course. Would you say someone who's not very good at maths will have trouble with this course? I hope not. So I've mentioned that there are a couple of points from maths which are useful, but the real mathematical knowledge that we require in this course is actually quite little. It helps to be familiar with like what matrix multiplication is. That's useful for one or two examples later on. But fundamentally, there isn't that much maths in this course. However, like what I mean by maths here is, knowledge from Math 1131 or equivalent. However, you do need to be able to reason about. You need to be able to reason about your claims and your arguments in a similar way that you would in the proofs section of discrete maths, and so in that sense, being able to reason about things like precisely and clearly, those kinds of skills that you develop in discrete maths, those are important here. Yeah. So I hope that answers your question, KA. Good at maths is a little, how to put it? It's a little non-specific for our purposes. You do need to be able to reason about things precisely and clearly, but you don't need to be able to solve quadratic equations very quickly. That's not the point of the course. Okay. Yeah, exactly. Faza has the right idea. We are problem solving, and you can use a computer and programming to automate some of that, problem solving for larger inputs, which means that really any problem solving can be related to programming, but it's not the main focus. Michael, can we use pseudocode? Try not to is our recommendation. The reason being that everyone has different conventions for what pseudocode is, and again, it's less easy to read and understand consistently than just writing. So, you will not be penalized for including pseudocode, but if you want to include pseudocode as a supplement to an already complete solution, fine. But it shouldn't be necessary for someone to read your pseudocode to understand what your argument is. Does that make sense? So you should describe the algorithm in words. If you choose to also include some pseudocode for confirmation, fine, but it's not necessary. Mel has a good idea. Make them choose each other's items, something like a cake problem. Yeah, that's a good idea. Yeah, exactly. A couple of you have recognized that this is a reskinning of a very famous problem. Gary, yeah, so we're going to have to talk about some of the details regarding items in a bit, but we'll get there. Riaz, what part of the textbook is relevant to the topic we're doing? This is already listed. So when you go to Moodle and look up the lecture slides, each of those lecture slides will also say KT chapter something, CLRS chapter something. And so that is telling you which chapters or which sections of the Kleinberg and Tados textbook and the CLRS textbook are related to the content covered in the lecture slides. Okay. So yeah, we're already doing that for you. And again, that's something that was requested in I think a My Experience survey or early on last year. So that's something that was given to us by that was requested by students. Can you release all the slides at once? No, because I'm still working on some of them. Uh, Again, there were some requests regarding a couple of the later topics, dynamic programming and Max Flow particularly, and so those are still in development, and they're not ready to release yet. Yeah, so typically the slides will be out like the day of, maybe the day before the lecture. If they are 100% ready before like a few days before the lecture, I'm happy to put them out, but I'll put them out as I go. If you use zero-based indexing, look, we ask that you don't go out of your way to differ from the notation used in the question because it makes it more difficult to understand your submission. We will do our best to follow any different convention that you might use from the stated one, but if you choose to use zero-based indexing in a question where it very specifically and clearly states uses one-based indexing in the question, I think you are mainly just making your own lives and our lives harder. So we ask you not to. is the main thing here. So yeah, we'll try not to deduct you, as long as what you're doing is clear. Usually, there's no added clarity from doing this. Okay. So hopefully that's answered your questions about getting started in this course. Again, there's been a few people ask how to do well in this course. Of course, this is a kind of vague question. It is hard to give a very specific answer to that. But the main thing I can tell you is practice, practice, practice. Right? The more practice you do, the better you'll improve your skills, which is the main focus of this course. Improving your algorithm design skills. Yeah. Okay. Right, it's been 10 minutes, so I guess we will get started again. In fact, if your knowledge of Comp 2521 or 9024 is rusty, this week is your chance to catch up on that. So in this week, so today and tomorrow's lecture content, we won't be introducing anything that you haven't seen already, with the exception of some of the complexity notation at the start of tomorrow's lecture. Some of that will be new. But really, out of the 4 hours of lecture content, only like half an hour of it is stuff that you haven't seen before or couldn't have seen before. So yeah, this is again a change that we've made in the last term or two. We've slowed week one down so that you can revise your earlier course. It used to be the case that tomorrow's lecture would have been jumping into new material. We're not doing that anymore, precisely so that you have some time to revise, do some tutorial problems from that first set, and make sure that you're on top of all your previous courses stuff before we get into new stuff. Okay. So yeah, if you're concerned about your knowledge of the previous course, of the prerequisite course, this week is your chance to catch up and to do the tutorial exercises and make sure that you're able to recall and use those ideas from Comp 2521. Okay. Let's get started. So, I want to start actually with one of the suggestions in the chat. This suggestion came in from... Let me find it. Actually, can I find it? I'm not sure. Chen Lifu asked, when is the recording submitted after the lesson? The recording is Oh yeah, yeah. The recording is available on YouTube immediately. Yes, Red Mobs asks, can we ask the thieves to select an item that they believe to be the most valuable? This is, I think this is this idea has some merit and also teaches you about some pattern that we have to avoid as well. So there's some good in there, and there's also something to learn from. Um, Certainly, you can ask them to select an item that is the most valuable to them. This is the basis of a greedy algorithm. It's a good start. However, I do also want to bring up when you propose something like this, you do have to think about, is this something that you can actually do? Is it a situation where we can ask both Alice and Bob, pick your favorite item and take that? What might be the problem with this suggestion? When might this not work? The issue here is, what happens if they both want the same item? Yeah? What happens if there's a single item which Alice thinks is the most valuable and Bob thinks is the most valuable, right? So if your algorithm says, if your algorithm says Alice and Bob each pick your favorite item, you do have to give some precise description of what happens when they both want the same thing. Yeah. So, this is the kind of thinking that you need to replicate when you go and write your own answers to assignment problems and tutorial problems and exam problems. Every step you do need to think about, is this something that we can actually do, and in all cases. There's some interesting ideas being proposed here as well. Things like tossing a coin for their common favorite item. This introduces an element of randomness, and that's something that maybe has some merit, but we aren't going to be talking about that in this course. Because in order to analyze a randomized algorithm like this, you'd need to do some statistics to find out with what probability certain people get certain things, and then that gets beyond the scope of this course. Okay? So, so I'm gonna, yeah, exactly. As soon as you're selecting item by item, you run into some problems. So I'm gonna give you the solution to this kind of famous problem, the cake problem, if you like, and then we'll discuss some of the disclaimers that we have to make here. So the solution, as Tim has proposed, for example, is that Alice splits the pile into half and half, so that she believes that both parts are equal value, and then Bob gets to pick either one of the two piles. Of course, Bob is going to pick a pile that he believes to have at least half the total, and Alice always thinks that the other pile is exactly half the total, which means that both people are happy. They both think that they have got at least half the loot. Again, there's no objective value to any of the items, so we do have to just work with their own valuations of things. And yeah, so this problem, again, is fairly famous. I hope some of you have seen it before. Now, there are some complications here, which we are going to ignore for the purposes of this problem. When we've said divide the loot into half and half, we've assumed that this is possible. Yeah? But since if we have discrete items, it might actually not be possible to do this. It might not be possible to form a pile that's exactly half the total value in Alice's estimation. Oh, sorry. Misclicked. The clicker is useful, but also I'm a bit clumsy, so I'll try not to do that too often. So, in particular, if we have n items exactly, and the ith item is VI in Alice's valuation, then a question of whether Alice can actually split the loot into two equal piles, whether it can be done and whether it can be done efficiently, are both interesting questions, and it turns out that we don't know. And what I mean by that is, certainly there is an option of try all the roughly 2 to the n ways of splitting up the items into two piles, and then count up the value of each pile and see if they're equal. So for n items, there are 2 to the n-ish ways to do this. unfortunately, we don't have a much better way of doing it. And again, it may be the case that in none of these 2 to the n separations that the size of the 2 piles is equal. Yeah, so if you're familiar with the knapsack problem, this is something that we're going to revisit in later topics. But yeah, so what I want to mention here is that if there are n discrete items that you either pick the whole item or not, or forego the whole item, it might not be possible to split the piles into 2 equal piles, and furthermore, it's not something that we can quickly determine whether it's possible or not to do. However, we're going to ignore that. So for the purposes of this problem, we're going to ignore any issues of discreteness. We're going to assume that we can always split up the loot into any fraction. For example, maybe they're not n objects, but rather n, buckets of liquid, and you can take any amount of the liquid from any bucket, right? So for our purposes in this problem, we're going to assume that each of the items can be distributed, can be divided into whatever fraction we like. Now, in this case, we're happy to do the two thieves version of the problem, where Alice splits the loot into 2 halves, and then Bob takes whichever half he thinks is better. But what if we extend the problem? What if we have 3 thieves? So in this case, Alice, Bob, and Carol have robbed a warehouse. There are n items. There are no objective values, so each of the 3 thieves has different valuations of the items. How do we split up the loot between the 3 thieves so that each of the 3 thieves thinks that they got at least 1/3 of the loot according to, again, their own valuation? How do we do this? Well, this is quite a bit more complicated. Yeah, it's a much harder problem. I think the natural place to start is, let's just extend what we did for 2 thieves up to 3 thieves. So in the 2 thieves problem, we asked Alice to split the loot into 2 piles and Bob to pick one of the 2 piles. What if we do something similar? Let's ask Alice to split the loot into 3 piles, and then both Bob and Carol get to pick from those 3 piles. So Alice splits the loot into piles X, Y, and Z of equal value. Bob and Carol choose which pile they want to take. Do we think that this algorithm is correct and complete? Does it answer the question? So Casper, before we get to your idea, which also is interesting, let's deal with this. What if Bob picks for himself and Carol picks for herself? Is this correct? Faza asked the important question here, and Wonsok as well. Yeah, the main issue here is, this is all well and good if Bob and Carol choose different piles, right? So certainly Bob and Carol are going to pick the pile that they think is the best. And I can guarantee that the pile that Bob picks is at least 1/3 according to Bob's valuation. Similarly, Carol is going to pick a pile that's at least 1/3 according to her own valuation. So if Bob and Carol each pick different piles, then the 3rd pile goes to Alice. Alice thinks they're all the same, so all 3 are happy. Yeah. If they choose different piles, they can just take their own, and Alice gets the one left over, and everyone's happy. But, as a few people have suggested now, there's a complication if they both choose the same pile. And indeed, the same kind of situation happens with Casper's suggestion, where Bob chooses for Carol and Carol chooses for Bob. Again, what if both of them pick the same pile? What if there's one pile that both of them think is really bad, and they pick that for the other person? Again, you're going to run into the same problem. Okay. So good, I'm happy that everyone's got the right idea here. So we do need to deal with this case where Bob and Carol are choosing the same pile. One suggestion for circumventing this problem might be, okay, say Alice splits it into X, Y, and Z. Both Bob and Carol want pile X. Well, then we can't give pile X to both Bob and Carol. So instead we're going to say, all right, pile X is on hold for a bit, but certainly Alice shouldn't pick pile X, right? This seems like a bad idea. If Alice is to pick pile X, then, both Bob and Carol are unhappy. So instead, because Alice doesn't care which pile she gets, she thinks they're all the same, let's ask Alice to pick one of the other two piles, say Y or Z. Then, if Alice picks pile Z, then we have two piles remaining, piles X and Y. Both Bob and Carol want pile X, but there's no reason why we have to keep this division that Alice decided. Instead, what we'll do is merge piles X and Y together and ask Bob to split it up and Carol to choose. Yeah. So shuffle and split again between just Bob and Carol using the same idea as the two thieves problem. So let me actually run a poll here. How do we feel about this? Do we think that the modified algorithm, where both if we think, let's try that again. So if Bob and Carol are to pick the same pile, then what we're going to do is ask Alice to pick one of the other two piles, and then the remaining pile, that is the pile that Alice didn't choose, as well as the pile that both Bob and Carol want, get combined together and split between the two of them. How do we feel about this? Are we confident that this is now correct? Surprisingly, the vote is, I think, exactly half-half. Oh, okay, the yeses have it. No, the noes have it. My bad. So, can I get a representative of either the yeses or the... Yeah, actually, let's get one of each. Can I get a representative of the yeses to argue their case? All right, Mal, I'm gonna keep you in mind for the noes. So, okay, yeah, let's go with Mal's suggestion. So Mal, I think, is one of the noes. Mal's suggesting that the newly created pile could be unfair to Alice. Or that, one of the other two piles is better than hers. But Depoys is correct. Alice is already happy. Alice doesn't mind which of the three piles she gets because she made the three piles. She thinks they're all equal in size or equal in value. So it's the criterion is not that Alice thinks she got the best of the three available piles, but rather that she thinks she got at least 1/3. So if she only gets 35%, but someone else gets ripped off for 5%, she doesn't mind. If she thinks she only got 30% and the others got 35 each, then she's unhappy. Yeah? So really there's no circumstance here where Alice is going to be unhappy as long as she's getting one of the three piles that she made at the start because she made them. She thinks they're all 1/3 of the total. So Alice is going to be happy with this situation no matter what. Yeah, exactly. Casper's correct. Alice got 1/3. Alice got one of the three piles that she started off with, and she doesn't really care how the remaining 2/3 is distributed, because again, the objective was that everyone should think that they got at least 1/3, and Alice certainly satisfies that. So, if there's going to be an issue with this modification of the algorithm, it's going to be that either Bob or Carol is unhappy. So some of you think that Bob and Carol are definitely going to be happy, no matter how we split it up, and a few more of you think that either Bob or Carol might be unhappy here, is how I'm interpreting the poll. Yeah, so who will split the new piles? Bob will split the new piles. So Alice will take something, and then Bob will split the remaining two, and Carol will take her pick out of those new two piles. Peter's, fantastic. I'm really happy to see. Yes, Deep Boys is correct. Alice got first dibs, and she made the piles, so she's happy. But Liz and Peter have the correct idea. Bob or Carol might be unhappy with what's left after Alice takes her pile. So I'm going to bring up one I prepared earlier. What? Oh no. Okay. Alright. I'm gonna have to redraw that because I've drawn it upside down. Oh no. I've never done that before. I've done heaps of here's one I prepared earlier, and I've never stuffed that up before. Yeah. You are encouraged to laugh at me. Alright, let's try that again. Yeah, I'm not gonna turn the whole thing around. That's a bad idea. I'll knock something over if I try to do that. Let me. Yeah, okay. Yeah, so my freehand circles aren't great. My apologies. Alright, let's switch over. To okay, it's because I made a mistake. I can't so mistake of spatial reasonings, shall we say. Alright. So there is actually a problem with this suggestion. What if we have 3 piles like this? So Alice makes 3 piles X, Y, and Z. And Alice thinks that they're all the same. Alice thinks that they're each 1/3 of the value. But Bob and Carol see it differently because again they have different valuations of everything, right? So Bob thinks X is half the total, but Y is only 10% and Z is 40%. Carol, on the other hand, agrees that X is the really good one, it's half the total, but she thinks it's the other way around between the other two. So Y is 40% and Z is 10%. Yeah? What's the problem here? If we execute the algorithm that we propose, then Alice is going to make these 3 piles, Bob's going to say, I want pile X, Carol's also going to want pile X. And therefore we say, okay, pile X is on hold, neither of you get it right away. Instead, Alice takes either Y or Z. Suppose Alice takes Y. That means this pile is gone. Yeah? Alice is happy because she thinks pile Y is 1/3 of the total. And Bob's also happy to split everything except pile Y with Carol. Because Bob thinks that 90% of the value is still there. However, Carol's not happy with this arrangement. Carol says that pile Y is gone, and therefore only 50 plus 10 makes 60% of the total is still remaining. And so when she splits that 60% of the total with Bob, she's only guaranteed to get 30% of the total, and so she's not happy with this arrangement. She could potentially get less than 1/3 of the total. And now you might say, okay, yeah, so maybe pile Y is bad, so Alice should have picked pile Z instead. Maybe we can fix this somehow. But of course, everything's symmetric, right? And as soon as you pick pile Z, then it's no longer Carol who's complaining. Carol's actually very happy. But Bob now says, oh, only 60% of the total is left. I'm not happy to split that with Carol. And so we have a problem. Yeah? Neither Bob nor Carol is necessarily satisfied. So, let me try that again. It's not guaranteed that both Bob and Carol are happy with this arrangement. They're not necessarily happy to split the biggest pile, in their common opinion, together with one of the other 2 piles. So, let me just have a read through the comments. Alice splits into 2/3 and 1/3, and then Bob chooses. Andrew, that's a really good idea. We're going to revisit that idea shortly when we get to the actual answer. Peter, in order for them to get over 1/3, the one picked second maybe pick the second highest value pile. I'm not quite understanding that. Perhaps you can clarify that in another comment. What if we ask Bob to redistribute the piles after Alice splits it up? Sure, but like, how is that different to just starting with how is that different to starting with Bob? Yeah? If we're saying ask Alice to make 3 piles and then ask Bob to rearrange those into 3 new piles, this is not doing anything different than just changing the names of the 3 people. So this alone doesn't really solve the problem. Yeah? So this is a really good idea and an intuitive one, but also one that doesn't work, which is, I think, illustrative of the ideas that we have to maintain as we do algorithms. We need to not be too easily convinced of the ideas that we have. Yeah, I think it's very easy to design this algorithm where you say, oh hey, there's a problem with doing the natural thing. You fix it, and it seems to work it seems to intuitively work, right? Certainly, if both Bob and Carol like pile X, then they should be happy to split pile X together with one other pile. But that isn't true. It's not true in all cases, at least. And we need to design algorithms which are robust to even worst case input. Yeah. So it needs to be correct in all cases. Yeah, and that's why this algorithm doesn't work. And it's a good example of why you have to be thorough in your examination of your own ideas. Yeah, exactly, Faza. If Alice is to take pile Y, then both Bob and Carol need to be happy with half of X plus Z. And that's not true in this case. Okay. So, I think it's time to switch back to the slides because we're going to now present the actual answer, which is something that I think a couple of you arrived at. So, first we're going to ask Alice to make a pile which is 1/3 of the total. And then we're going to get Alice to ask, we're going to ask Bob, are you happy to not have this pile? So we're asking Bob, is this pile that Alice has made less than 1/3 of the total? If he says yes, that means he thinks 2/3 is still out there. In other words, he's happy to split the rest with someone. So if Bob says yes to this question, that is X is less than 1/3, then the remainder of the loot is at least 2/3, and he's happy to split that with someone. In which case we should then ask Carol the same question. If Carol also thinks that X is at most 1/3, then she's also happy to split the rest of the total with someone else, namely Bob. So if both Bob and Carol say yes, then that's great. Alice takes the pile X, Bob and Carol splits the rest. But in fact, even if Carol says no, we have a way around this. Because now Carol thinks that pile X is actually valuable. It's something that she would be happy to take. Great, she can have it. Because Alice doesn't care about, Alice thinks that the rest is exactly 2/3, so she's also happy to split that with Bob. Yeah? So, if both Bob and Carol don't like the pile, great, Alice can have it and they can split the rest. If Bob doesn't like the pile, but Carol does like the pile, great, Carol can have it, Alice and Bob split the rest. So as long as Bob doesn't like this pile that Alice made, we're good. We've yet to discuss what happens if Bob does like the pile. Alright, so let's just confirm that we're happy with this so far. As long as Bob's happy to split the rest with someone, we can solve the problem. Next up, what if Bob likes this pile? So Bob is not happy to split the rest with someone. Well, This means that this pile X that we made is 1/3 according to Alice's valuation and greater than 1/3 according to Bob's valuation. Well, this should seem familiar. We're in a case where one person likes the pile more than another person. What we're going to do is ask Bob to take this pile and throw out some stuff until he thinks it's only 1/3. This means that less that stuff that he got rid of, Alice now thinks the value is less than 1/3. But now we're in the same situation as before, right? Bob thinks this pile is exactly 1/3. Alice thinks it's less than 1/3. So Alice is happy to split the rest with either Bob or Carol. And now we ask Carol about the modified pile. And we approach it as before, but with Alice and Bob's roles reversed. Yeah? So again, the symmetry of the problem is the most important thing here. Yeah? There's nothing special about the names Alice and Bob. We could have just as easily switched them around and started with Bob, and that's exactly what we effectively do at the end of this. All right. How do we feel about that? Nothing in the chat, so just dwell on this for another few seconds. Let you get any questions in before we move on. All right, so yeah, what if Bob lies about the pile value being 1/3? Yeah, no, that's fine. Take your time to read through this. That's okay. So we're gonna assume that everyone's honest here. I'm aware that they're thieves, and so we perhaps shouldn't assume that, but yeah. The point is that if we make a pile that, like earlier, we saw how to solve the problem. If Alice likes the pile, or likes the pile exactly 1/3, and Bob doesn't like this pile. In this situation, we're going to make a new pile where Bob thinks this pile is exactly 1/3, and Alice thinks it's less than 1/3, which means we have exactly the opposite situation to what we had before. Yeah. So, yeah, look, Alice evaluates the new X as less than 1/3, but we never actually give Alice the pile X. So she's happy because she's always splitting the rest with someone. Yeah? So I hope that answers your question, Montauk. Alice doesn't like pile X, the new pile X at least, and so she always ends up splitting everything except the new pile X with one other person. Yeah. Bob isn't just taking the greater pile because we're not letting him. Because if we just let him take the good pile, then there might not be enough left to split between Alice and Carol. Yeah. Yeah, so, All right. Cool. So I think, again, the important things to take away from this is symmetry is a very useful technique in solving problems. We have distinguished roles here, Alice, Bob, and Carol, but they are all actually the same. Just we gave them an order arbitrarily, and we can change that order if we need to. Yeah. So okay, I'll let people continue discussing this as we go, but we do need to move on. However, there's an important idea here, which is, okay, great, we went from 2 thieves to 3 thieves. What about 4 thieves? What about more thieves? So as an exercise, think about generalizing this to n thieves. And I think this is going to be one of our first forum challenge posts, I guess. So this term we're going to try seeding some engagement with some challenge questions or discussion posts that we'll post ourselves as staff. Of course, you are also welcome to contribute your own. But so we'll discuss this problem more on the forum. But as a hint, you should observe some kind of recursive idea going on with 3 thieves. Maybe we can nest that recursion some more when we go up to 4 and more thieves. Robin, this is why you robbed the bank by yourself. Yeah, fair enough. Okay, so at this point, we do need to move on to giving you an overview of proofs and the role of proofs in algorithm design. So when we make claims about our algorithms, whether that is about the correctness of the algorithm or about the running time or time complexity of the algorithm, we do need to reason about the correctness. The guidelines that we give you in the assignments are that you have to justify the correctness and the time complexity of your algorithm. Now, does that mean give a formal mathematical proof? Not necessarily. As a general rule of thumb, it's a question of common sense. So again, our standard in this proof is always that you have to justify correctness and time complexity. In many situations, this is just write a sentence that gives a reason as to why you're doing what you're doing, or why the claim that you've made that your algorithm runs in quadratic time is actually true. So explain that in a sentence or a couple of sentences. In some situations, however, it will not be clear from a sentence or a couple of sentences why exactly that is true. It might be something that's not obvious at all. And in those situations, that's where we use formal proofs in the same way that you would have done in maths courses, including particularly discrete maths, and similarly in Foundations of Computer Science. So here's an example of an algorithm that hopefully you're all familiar with, which is merge sort. It's going to be an algorithm that's important to us next week as well as tomorrow. So we're presenting some pseudocode just because, again, you're all familiar with merge sort, I hope. If you want to sort the section from left index L to right index R, we will simply there's a base case where you do nothing if L and R are equal. Otherwise, find the midpoint, merge sort the first half, merge sort the second half recursively, and then do some merging procedure, which, again, I hope you're all familiar with. Now, some claims about the time complexity, the running time, as well as the correctness of this algorithm. First of all, the depth of recursion is log base 2 of n. Hopefully this is clear. We start off with an array of size n, and at every level we halve the size of the subarray that we're working within, and therefore you can only halve that n array log base 2 of n many times. Right? Hopefully that's clear enough. If we keep halving, we will, after log base 2 of n many halvings, we will get down to singleton subarrays where there's no further recursion. So the depth of the recursion is log base 2 of n. Furthermore, at every level of the recursion, all the mergers put together take linear many steps. Again, since you know what the merge procedure is, this should hopefully not be surprising to you. To merge two arrays each of size half n takes about n many steps. To merge 4 arrays each of size n over 4 in pairs again takes about n many steps, and so on. So there are log base 2 of n many steps, each taking, the log base 2 of n many levels, and at each level we spend linear time, which means the total time taken by this will be n times log base 2 of n. So therefore, merge sort definitely terminates, the recursion doesn't go forever, and the termination always happens within big O of n times log base 2 of n many steps. That up to this point, we've talked about the complexity, or the running time of the algorithm. We have not yet talked about the correctness. Sure, you can do this kind of recursion and merging, but why does it actually get you a sorted array at the end? Well, the important thing is that we are always, how to put this? As we build from the bottom up, we are merging, right? We start from singleton arrays, which are by definition already sorted. And anytime you merge two sorted arrays using the well-known merge procedure, the result of that is also a sorted array. Which means that as you build up, you're going to get larger and larger sorted arrays, and the final result, which is the very top level n array, that also will be sorted. In essence, this is a proof by induction. But since this is so straightforward, in this course we would consider this one or two sentence explanation to be sufficient. Yeah. So we do not need you to write up a formal proof by induction using this notation that you would have done in high school, and I suppose also in Math 108 for a simple statement for a simple idea like this, that merge sort produces actually sorted arrays, one or two sentences of reasoning is fine. There's no need for further detail here, right? So we're not writing proofs for the sake of writing proofs. We are writing proofs when something is actually not obvious. Big omega and big theta notations, yes, we will care about those. We'll see those tomorrow. Okay, so, all right, so I've told you that proofs are useful, but also I've shown you that sometimes we don't need proofs. So why did I say proofs are useful? In what circumstances do we actually need to include a formal proof of the correctness and the time complexity of the algorithm? Well, it's when it's not clear from the description of the algorithm that the claims are actually true. So maybe we can describe an algorithm, but it's not clear from that description as to how many steps it takes. Maybe it from the description it might not be obvious that the algorithm actually terminates. It might be plausible for the algorithm to enter an infinite loop. Maybe it's not clear how many steps the algorithm takes. Certainly some algorithms you can simply count the nested loops and take n to the power of that, and that's obvious. But this is not applicable to all algorithms. Other times, it may appear at least that the algorithm takes exponentially many steps, or whatever other formula which is beyond what is desired in the question. Finally, you can describe an algorithm and say that you're calculating something, but why is that something the actual answer to the question? You, again, might need to provide some formal reasoning for this. And so as an example of all of these, we're going to demonstrate the stable matching problem. So in situations where it's not obvious that the claims you're making are actually true, you may, and you typically need to provide an actual proof of your claims. Yeah. So we'll prove non-trivial things. Okay? And hopefully this is obvious that what you call trivial might not actually be trivial. So be careful, make sure that you're, again, self-critical in your reasoning. I think this also comes back to this idea, right? It's easy to convince yourself that an idea you had is actually correct, and not fully think through all the counterexamples. So I can, again, suggest that you be as critical as you can of your own work, try and disprove your ideas, because try and construct counterexamples that don't fit the typical examples that you might have in your head. And once you are really convinced that, hey, no, it's actually quite my algorithm is actually robust to all the different kinds of inputs that I could get, at that point you can now start thinking about formalizing that proof, providing reasoning as to why it actually does what you think it does. Okay, so as an example, we'll present the stable matching problem. So this is a famous problem. Suppose we have n hospitals, and there are n new doctors who have just graduated, and we want to assign doctors to hospitals in such a way that each hospital gets exactly one new doctor. And the way the input that we get is, for every hospital, they tell us a list of their preferences. They rank all the doctors from 1 through n. Every doctor also ranks the hospitals, again, from their favorite hospital number 1 to their least favorite hospital number n. Now, since we have these two n many preference lists, it's not necessarily possible to make everyone as happy as we can, right? We can't necessarily give every hospital their favorite doctor or every doctor their favorite hospital, because there might be clashes, right? Maybe there's one new doctor who's really good and all the hospitals want that doctor. They can't all have them, yeah? So we lower our expectations a bit. Our algorithm should not necessarily produce an output where everyone gets their first preference, but instead we only require that the matching be stable. Stable means that there's no hospital doctor pair who are unhappy with the assignment and want to leave the system. So we need to pair hospitals and doctors so that there never arises a situation where Hospital H has Dr. D and Hospital H dash has Dr. D dash, but H and D dash would both prefer to leave the system together. Yeah? In other words, if Hospital H were to prefer D dash to their doctor, and D dash would prefer this hospital, a different hospital to the one they got, then you can see that in this situation, both Hospital H and Dr. D dash will say, hey, no, your system's rubbish, we're doing it on our own, I'm just going to hire this doctor directly, and you can sort the rest of them out. We don't want this to happen. Make sense? So our goal is to produce a stable matching, one in which no such unmatched pair is better than the matchings at both ends of that pair. Right? So here's some examples. Suppose we have Hospital 1 and Hospital 2 who both prefer Doctor 1 to Doctor 2. We also have Hospital 1 preferred by both doctors. In this case, there are two possible matchings. Certainly we could pair Hospital 1 with Doctor 1, Hospital 2 with Doctor 2. This is a stable matching. There is no unmatched pair in this who would prefer to leave the system. However, if we were to do the other pairing where Doctor 2 goes to Hospital 1 and vice versa, Doctor 1 goes to Hospital 2, well, this is not a stable matching. Because Hospital 1 is going to say, why'd you give me Doctor 2? I prefer Doctor 1, and also Doctor 1 wants to be at my hospital rather than the one they're at. So, your system's rubbish. Hospital 1 is just going to say, nah, we're going to hire Doctor 1, they're going to take us, and you can sort the rest of them out. Yeah? So, this is the sense in which the second example here is not stable, but the first example is stable. Yeah. So, there's some discussion about big omega and big theta. We are going to talk about that tomorrow. Correct. It's they don't all have to be as happy as possible, just that no unmatched pair should be should be preferable to both ends of the unmatched pair. Yeah. So here we've done one example with two hospitals and two doctors, so where n equals 2. But there are other ways that the preference lists could look. We could instead have a situation where Hospital 1 wants Doctor 1, but Hospital 2 wants Doctor 2, whereas Doctor 1 wants Hospital 2, and Doctor 2 wants Hospital 1. Well, this is a bit confusing, right? In terms of the hospital preferences are in conflict with the doctor preferences. This situation is actually fine no matter how we do the assignment. If we place Doctor 1 at Hospital 1 and Doctor 2 at Hospital 2, then why is this stable? Why is the middle diagram here a stable matching? Can someone give me a concise reason as to why the pairing where Hospital 1 gets Doctor 1 and Hospital 2 gets Doctor 2 is a stable matching? Yes, Peter's correct. Both hospitals are happy with the doctor they got. Yeah? So it's not that everyone's unhappy. Certainly both doctors are unhappy, and either of those doctors would like to swap, but neither of the hospitals want to swap. And so there's never going to be an unmatched pair which is preferable to both ends. Yeah? Hospital 1 doesn't want to leave the system with Doctor 2 because they're happy with the doctor they got. And so when you go to the other example, the other kind of matching that we could get here, where Doctor 1 gets placed at Hospital 2 and Doctor 2 gets placed at Hospital 1, here both hospitals are unhappy, but both doctors are happy, which means, again, this matching is stable. No hospital-doctor pair that's unmatched is going to leave the system. Yeah. So in this situation, either both hospitals are happy or both doctors are happy. Either way, it's going to be stable. So, as an exercise, there are two more cases to consider where n equals 2. So you can have a go at doing those yourself on pen and paper. Yeah, so Ka, as long as one side is entirely happy, as long as one side all got their first preferences, that's definitely sufficient to make the matching stable, because no hospital is going to leave if all the hospitals got their first preference. But this is not the only way that a matching could be stable. Yeah. So it's kind of hard to demonstrate because you'd need larger lists, and at that point the amount of input also gets a bit difficult to show. But yeah, like if one side is perfectly happy, it's definitely going to be stable because no hospital would leave if they already have their first preference. On the other hand, there can be situations where they didn't get their first preference, but they're still happy with the one that they have rather than anyone else they could hire. Yeah, why do we value the hospital's preferences over the doctor's? We don't. They're equally important. Yeah. The important part is that there's never a situation where an unmatched pair is better than both the alternatives, like both the existing alternatives. So, yeah, I'll leave this as a reference. You can write up like this. This write up covers all the situations where n equals 2. But you can read that in your own time. This doesn't necessarily generalize. Now that hopefully most of you have an understanding of the problem, we're going to generalize this to not just n equals 2, but general n. And so we're going to end up developing this so-called Gale-Shapley algorithm. Supposing there are n doctors and n hospitals, well, we need to pair them up somehow. And so our first instinct might be, let's consider all the pairings of hospitals and doctors and then check each one for whether it's stable or not. This is the most simple brute force, naive kind of algorithm you could come up with. And so the first instinct should be, okay, great, but that's really slow. And let's quantify how slow that is. The way we're going to do that is we're going to work out how many matchings there are to consider without thinking about the preferences, and then see whether you could work your way through each one of them and still have an efficient algorithm. The issue here is that if there are n hospitals and n doctors, without worrying about the preferences, there are n factorial different matchings that we could consider, right? Doctor 1 has n choices, Doctor 2 has n minus 1 choices, Doctor 3 has n minus 2 choices, and so on. So, in fact, there are n factorial many hospital-doctor pairs to consider, and so any algorithm which goes through each one of those n factorial many matches is going to be very slow. For context here, if n equals 70, so 70 hospitals and 70 doctors, we're now dealing with 70 factorial, which is about 10 to the power of 100. Whereas the algorithm that we're going to end up developing runs in n squared time. So it's a difference of 5,000 versus 10 to the power of 100. It's the difference between milliseconds and life of the universe. So to give you a approximation for n factorial, maybe it's more easy to think of it as an exponential. Here we can use Stirling's formula to approximate it as n over e to the power of n. Again, something that you may be familiar with from first year maths. This is a point of more trivia than anything. Certainly n factorial is already really big. You should be familiar with the fact that factorials grow even faster than exponentials, and so this is even more than exponentially many in n. All right, so certainly we can't just churn through the matchings one by one. And we also have this other concern. Sure, the question asks us to find a stable matching, but are we sure that there is a stable matching? Is it possible that for some n lists of hospital preferences and n lists of doctor preferences, maybe there isn't any stable matching? Well, we're going to see that no, there is always at least one stable matching, but it's not at all obvious why this is the case. And in fact, we're going to demonstrate this mostly by stating the algorithm and then reasoning as to why it produces a matching which is guaranteed to be stable, thus proving that a stable matching exists. It's, again, not at all obvious from first glance at the problem that the problem's actually solvable. Okay, let's continue. So we mentioned now that at this stage we don't have any confidence in saying that there is even a stable matching out there, and we also know that the number of matchings that we should consider is really, really, really large. So the problem of finding a stable matching in a reasonable amount of time, in some that this is a tractable problem, this seems remote, right? But in fact, we can do this, and we can actually do this surprisingly quickly using the so-called Gauss-Shapley algorithm. So what we're going to do is we're going to go through a sequence of stages where we form partial matchings, and sometimes we will unmatch and rematch. So we'll edit the existing matching. We're going to need some terms for this. So in this algorithm, we will refer to hospitals who don't have a doctor yet as free hospitals. And hospitals will be offering jobs to doctors. Doctors will decide whether or not to accept the offer. Once you accept a job offer, you can rescind that acceptance and take a different job. So initially, all hospitals will be free. There will be no pairing at all. And then as we go in each stage, there will be some job offers made to doctors, and those offers might be accepted or declined. All right? So let's have a go at stating this algorithm. I want to be clear, by the way. As we present this algorithm, many of you will be thinking, I don't know how I would have thought of that. Yeah, that's fair enough. I too have the same thought looking at this algorithm. It's not intuitive, and it took designing this algorithm is a difficult problem beyond the scope of anything that we'd ask you to do in this course, except where it's building directly off stuff that we've seen in lectures, right? So I would not expect you to solve this problem just from the problem statement. It's a really hard problem. So please, please don't think of this problem as an example of the type of thing that we are expecting you to be able to solve right away. This is more illustrative as an example of when claims that we are making about our algorithms are not obvious and how we prove them. Okay? So, the algorithm goes like this. Again, I'm going to use pseudocode so that I can state it concisely, so that it fits on a slide, basically. In practice, in an assignment submission, you would write this in full sentences. But while there's a free hospital, which has not offered jobs to all doctors. So again, free hospital is one that's not currently employing anyone. And so we're going to say, as long as there's some free hospital that doesn't have a doctor and hasn't given out a job offer to every single doctor in the system, we would say to one of those free hospitals, say H, offer a job to the next highest ranking doctor to whom you've not previously offered a job. So you say, okay, maybe this hospital has offered jobs to doctors 1, 2, and 3 on their list, and they still don't have a doctor employed, so tell them to offer a job to Dr. 4 on their list, their fourth favorite doctor. Now that job offer is sent, we will say, this doctor, if that doctor hasn't received an application yet, then they just accept the job offer because a job is better than no job, right? In this case, this new hospital H and the Dr. D who they offered the job to and the job was accepted, great, we can pair them up together and everyone's happy. Otherwise, if Dr. D has been offered a job previously, then we'll claim that they're already in some pair with a different hospital H dash. Now, Dr. D has a good choice, right? They already have a job at hospital H dash, but they're being offered a job at hospital H. And so which one of those two offers will they take? Well, they take whichever they prefer according to their own preference list. So we ask Dr. D, you already have a job at hospital H dash, there's a new job offer from hospital H, which of those is higher on your preference list? If Dr. D prefers the new hospital, they will rescind their acceptance of the job from hospital H dash, and they will accept the job from hospital H instead, which means that the pair H dash and D is deleted. H dash goes from having a doctor to not having a doctor, so they are now free, and the new pair H and D is formed because Dr. D is now placed at the hospital H. On the other hand, we might have the other case where H is lower on her preference list. Maybe she's very happy with the job she already has and she doesn't want this different hospital H. In that case, she's going to decline the offer. Which means that hospital H remains free and now they have one more, they've marked off one more of the doctors on their preference list. Make sense? So this is the algorithm. Now, this algorithm leaves some details to be confirmed, right? Reading this algorithm, it's not clear that it answers the problem, it's not clear that it terminates, it's not clear how quickly it terminates, but we are going to address all those questions. Now, I will just mention we are over time, so if you have things to get to, by all means, you can leave and watch back the recording later. I'm hoping to wrap up within about 20 minutes or 30 minutes at most. Unfortunately, the admin stuff dragged on a little longer than I had anticipated. Sorry about that. In my experience, most of these lectures don't go over time, but this one can do sometimes. Okay, so let's get started. So this algorithm, as described, doesn't obviously terminate. It seems plausible, at least, that this might go on forever. It doesn't obviously run it doesn't obviously run quickly, because there seems like there might be a lot of runs of this loop. We haven't really quantified how many runs there will be. And it's not obvious that this produces a matching of every hospital with every doctor, let alone a stable matching. So we will need to confirm all of those things. So the first claim that we're going to check is about the running time of the algorithm. We're going to claim that the algorithm terminates after at most n squared many rounds of the while loop, and in fact that, which means it does terminate, and it terminates reasonably quickly. So the proof is actually reasonably straightforward. In every round of the while loop, we get one of the free hospitals to offer a job to one of the doctors. And a job offer is only made to a doctor that they have not offered that same job to previously. Yeah? If you're hospital H, you're meant to offer a job to the next ranking doctor on your preference list. Once they say no to that job, you don't ask them again. Even if they say yes and then decline it later, you don't ask that same doctor again. Yeah? Which means that every hospital offers the job to their first preference, and then to their second preference if necessary, then to their third preference if necessary, and so on. They only offer the job to each doctor at most once, which means we have n hospitals, each making at most n different job offers. So, in total, the number of job offers, and therefore the number of times the while loop runs, is at most n squared. Are we happy with this? So the algorithm actually is guaranteed to terminate after n squared many rounds of the while loop, and that's the only part of the algorithm which involves any repetition All of the else is just conditional kind of branching. So we know that the algorithm terminates and terminates in n squared rounds of the while loop. The next claim to confirm is that the algorithm actually produces a matching. So we have hospitals and we have doctors. It's not obvious that at the end of this, that every hospital actually gets a doctor and vice versa. Yeah? It might, if we just have a look back at the statement, it might be possible that this while loop terminates not because there are no free hospitals, but because a free hospital actually offered jobs to everyone, and therefore it's not eligible for continuing the loop. Yeah? So we need to confirm that that this algorithm produces a matching, and to do so, we need to make sure that when the algorithm finishes, it's because there are no free hospitals, not because there are free hospitals, but those free hospitals have offered jobs to everyone. Well, why are we guaranteed this? Why do we know that at the end there are no free hospitals? Suppose the contrary. Suppose that there is a free hospital, but it did offer jobs to everyone, and therefore it's not eligible. Well, we're going to have a problem here. If the while loop terminated with hospital H still free, well, that means hospital H offered jobs to everyone. Yeah? Remember, at every stage, they offer a job to the next highest person on their list. So this means they offered a job to everyone. And the only reason you get declined when you're a hospital offering a job to someone is if that doctor already has a job. So they got declined by every one of the N doctors, which means all N doctors have jobs. But they all have to have jobs at different hospitals. And there are only N hospitals. And so we have a problem, right? Every doctor is paired with a hospital, and there are only N-1 other hospitals, so there's a contradiction. So this kind of proof by contradiction is a very useful idea. We make a claim, and it's most often the easiest way to prove this is to assume the opposite and show that this is impossible. Exactly, the least, like loosely speaking, a very unappealing hospital might get declined by several of the potential doctors, but eventually they're gonna offer one of their latest preferences, like one of the last preferences, and that doctor might not have other choices either, right? That hospital has to be taken by someone, otherwise one of the doctors is going to be unemployed. Yeah? All right. So we've confirmed now that this algorithm terminates after n squared runs of the while loop, and it produces a matching. It matches up every hospital with exactly one doctor. But we haven't said anything about this being stable or not. And that's, again, not obvious. So, how do we prove this? Well, we need to analyze the algorithm as stated a little closely. The doctors all start initially unemployed, but they kind of climb their way up, right? The first job offer they take, no matter who it's from, they take. The first job offer they get, no matter which hospital it's from, they take that job. And then if they later get even better jobs, they're going to climb up. They're going to go up their preference list of hospitals. Yeah? So they might start even at their least favorite hospital, but slowly they'll only move to better hospitals as the algorithm runs. The situation for hospitals is the opposite. They start with their favorite doctor and then get declined until eventually they get paired with a doctor. That doctor might later rescind them, and then the hospital has to go to even lower doctors on their list. Which means a hospital starts free, and then as it gets different doctors, those doctors will always be in decreasing rank according to the hospital's preferences. These two observations will be really important to our proof. Again, we're going to use a proof by contradiction. Suppose that the matching is not stable. That means that there's a hospital-doctor pair who would prefer to leave the system. In other words, we've matched together hospital H and Dr. D, hospital H dash and Dr. D dash, but H prefers to have D dash over D, and D dash prefers to have H over H dash. Why is this impossible? Why could this never have been constructed as from our algorithm? There is a fundamental problem here. H ended up with D even though they preferred D dash, and D dash ended up with H even though they ended up with D dash even though they prefer H. Well, remember, each hospital goes through their preference list from first to last, yeah? Which means that they offer the jobs to their favorite doctors all the way down to their least favorite doctors. And since hospital H likes Dr. D dash better than they like Dr. D, that means that they must have offered that job at some point. Yeah. So let's examine what happened when that job offer was made. Let's examine what happened when hospital H offered a job to Dr. D dash. Well, there are two cases here. Either Dr. D dash accepted the job or they declined the job. Well, let's say this. First of all, let's deal with the second of those cases. Why would Dr. D dash decline the job offer from hospital H? If they're declining that job offer, it's because they're already at an even better hospital than H. But then how could they go from an even better hospital than H to later being at hospital H dash, which is even worse than H? This is impossible because doctors only ever climb upwards. On the other hand, could Dr. D dash have accepted the job offer from H? Well, this too is impossible because if they've accepted the job offer from H and they end up later on at a hospital H dash, which is worse for them, this again couldn't have happened because again, doctors only ever go to even better hospitals. This is not possible. So in both cases, Dr. D dash can't have got an offer from hospital H but then end up at an even worse hospital H dash, and therefore we have a contradiction. Yeah, so hospitals start out at the happiest, where they're offering jobs to their favorite doctors, and they work their way down. Doctors start off at the least as unhappy as they ever get, and they only ever get better after that. And this kind of increasing situation guarantees that we never finish with a pairing that is unstable. Let me put that again. This guarantees that we never finish with an unmatched pair, which is preferable to both parties because, well, when that pair was a candidate, we chose not to match it or we later broke it. And either way, that doesn't happen. Okay, so again, it's useful to understand this proof, to understand this algorithm and what it does and why it does what it does. And variations on this algorithm are within the scope of the course. However, the key takeaways from this are you can, in many of these problems, you may have to describe an algorithm, but that algorithm might not obviously do what you want it to do. It might not obviously solve the problem correctly, and it might not obviously run within the desired time complexity. These are the situations where we need to write formal proofs using techniques such as contradiction and induction. Because, again, if it's not obvious that something's true, that's when the formal reasoning is really important and where we can precisely argue as to why our claims are actually well-founded. Yeah, we are over time, sorry. We're going to be wrapping up right now. So I'm going to leave you here with a puzzle. So in each set of lectures, we'll finish with a puzzle, which I think is a nice way to practice your problem solving in a less formal kind of situation. Again, feel free to discuss these on the forums. They always get plenty of engagement, which is nice. So again, some of you who do these things for fun may be familiar with some of these, but So yeah, we have a party where Tom and Mary attend with 9 other couples, and we're interested in handshakes between the unfamiliar people. And so we count up the number of handshakes that each person did, and we can deduce how many hands Mary shook and how many hands Tom shook. All right. So you can have a go at this, as well as the assignment questions, which are out now. Tutorial questions should be out shortly tonight, and tutorial solutions will be released in a couple of days. We'll reconvene tomorrow morning at 11, where we will be going over some preliminaries, so some mathematical fundamentals as well as complexity analysis, and we'll also be giving an overview of the content that we need to retain from the previous course, Comp 2521 or 9024. So that will give you an overview of what's assumed that you know in this course that you can use without reference, and give you a starting point for any revision that you might have to do. So yeah, again, no new material this week, just minimal new material at least, but hopefully a taster of what's to come. Right, and then yeah, we'll be having a consult tomorrow afternoon at 2:00. Okay. All right. Someone posted the solution in the comments of this video. All right, I'll have a look. But for now, that's all we've got for today. Sorry for going over time. Again, hopefully this won't happen too often. And I will see you guys tomorrow morning. Bye-bye, everyone.